Substrate provides mechanical support and electrical common point. Now some of the complex processors, if we see Pentium 3, Pentium 4, these are the level of transistors, 28 to 42 millions, die size 105 to 146 millimeter square. It can operate at 1.65, 1.5 volts. Now, in fact, the latest VLSI devices, they can operate even at 1.1 volts. And attempts are going on for less than that. So this is a microscopic view of some complex processors. So our ultimate objective is to draw polygons that represent layers deposited on the substrate. Like when you talk about VLSI design, it consists of a number of circuits, and the circuits ultimately leads to the transistors and how they will be laid out on a silicon wafer that is described by this diagram. So that is the ultimate objective which will be given to the fab manufacturer. Fab stands for fabrications, for making the chip. So manual layout design is obviously, it's not only practical, it's impossible now. And design complexity, manually drawing layout for a billion of transistors would take too long time. As I said, that is virtually impossible. So all that we require some kind of design automation tool, which are known as EDA, Electronic Design Automation Tool, or computer-aided design, the same basically. So using those tools, we'll be able to make the VLSI chip design. Slowly we'll go, how it will be made possible. So design automation, mostly on low-level logic synthesis, standard cell layout, straightforward solution. Now, what are standard cell layout we'll be discussing subsequently. So our dream is basically totally automated design flow, from high-level description to physical implementation. So we'll be describing your design ideas in a very high level, and that could be translated onto the layout. Okay, and high speed, low power, and low die size. These are the ambition. So speed means the performance, low power dissipations, and low die size. The size of the chip will be very small, and less time to market. Less time to market is possible if the entire design process can be completed in a less amount of time. Because today's world, especially after globalization, is very, very competitive. So all the companies, they will try to come to the market very, very fast. And for that, we have to take the help of design automation tool, which will help to design at a shorter time. That's very important. So what are the VLSI design opportunities? If we just look at the VLSI world, we will find right from 3G mobile to high definition televisions, audio video applications, wireless computing, software-defined radio, voice recognition, military applications, medical applications, and whatnot. Out of that, almost 85% markets are occupied by the consumer electronics, where the VLSIs are used. And state of the art, what are the VLSI design state of the art? System on chip, single chip solutions, digital signal processor, general purpose processors like Pentiums, memory, analog devices, okay, wireless communications, special purpose I/O. So now let's look at the overview of VLSI design flow. At the top, if you see this design abstraction level, so at the top level, what we require? We need to design a chip. Now, chip consists of what? A number of modules. Okay. Like, let's say we are talking about a processor chip. It consists of ALU, registers, etc. So this can be viewed as modules. Each module consists of a number of gates. Now, gates consist of what? Transistors. Transistors in the physical level, basically the devices. P, N, like here gate, drain, source, and how they're made. So right from the top level to bottom up, if we just go slowly, ultimately what you have to do, we have to go to the device level. That is the ultimate level. And VLSI design tool will make the layout of the devices and how they are interconnected among themselves. That is a simplistic form of VLSI design. So the design cycle is some specifications will be given, and from the specifications a chip will be designed. So input is the specifications and output is the layout of the chip, and that is the task of automation, design automation tool that will do for you. So larger number of devices, optimization requirements for high performance, time to market competitions, cost. So these are very important things. That means user will give the specifications, and getting the specifications using the VLSI design tool. Tools are nothing but the software. The layout will be generated by the tool. So layout indicates how these devices are interconnected and what are the pattern of the chip. Pattern in the sense of layout. So design cycle is like that. First, number one, system specifications, functional design, then the logic design. So functional design is what? From the specs, what are the basic units like arithmetic unit, registers, counter, etc. Then the logic design, logic to circuit design, circuit to physical design. After doing that, there is a requirement of design verification, whether it's correct or wrong. Because in case the design is faulty, then after manufacturing, entire thing will be faulty, and it's a huge loss from the financial point of view and time. So after design verifications, it will go for the fabrications. Once the chip will be fabricated, it's manufactured and will be encapsulated. They need to be packaged. Then again some testing and debugging has to be done before it's going to be shipped. So physical design converts a circuit description into a geometric description. That means right from the specifications, ultimately what you'll be getting, will be getting the geometric description. Just let's have a look at this one. So this is the basic description of the chip. And so these are the basic steps in the physical design cycle: partitioning, floor planning, routing, and compactions. I'll show you through this diagram. Now let's say you are a VLSI designer. Okay, let's start here. So design entry. Design entry means here you will be writing your code using a hardware description language. There are different hardware description language like VSDL or Verilog or System C. Using one of these languages, you describe your hardware. That means, first, before that, you have to make your design schematic. Okay, let's say there are some different registers, ALU, control unit, everything is there that you have designed. And verbally, those design you have to describe in terms of hardware description language. Then you get your synthesis. After synthesis, you will get some netlist. As the diagram is given at the right hand side, some block. Now, here the advantage of getting this netlist is you can test them separately. Okay, so this is called pre-layout simulation. Through simulations, you can check, and also you can partition the system. Yes. Then floor planning means how they'll be placed on a given area. Silicon. So here the optimization comes into the picture. How efficiently you will replace all these things. For an example, in a classroom, there are a number of chairs, tables, etc. So how effectively those chairs and tables will be placed so that the area of the room can be used very, very efficiently. Exactly here also the same thing. So within the silicon area, how this modules will be placed and will be interconnected. It's called floor plan. But today, the technology is so advanced, we don't have to do these things. Earlier, in fact, like people like me, some 25 years, 30 years back, when we used to design this VLSI, the tools were not that sophisticated. We had to do manually many things. And it used to take long time for designing, for floor planning, then placement, routing. So how they will be placed. After planning the floor, that means after planning the silicon area, how they'll be placed and how they'll be routed, like how that means how they'll be interconnected. Then get the circuit extractions. Again, do this simulations by generating some test patterns and check whether it's working properly or not. So it's a huge process. Now, entire thing now has been automated. So VLSI design tool, today's engineers, what they have to learn efficiently, how to write the codes. But before that, you must have to know what is the domain areas. So domain knowledge is very important. So using the domain knowledge, you write the code, what we call design entry, and follow the processes. So here, you need to acquire some skills to understand the VLSI tools and to use them in an efficient manner. Finally, what you will get? You will get finish means you will get the layout, what we described earlier, the pattern. Once again, I'm going. The final thing will be like, but it's much more complicated than what is given over here. This is a simplistic form. So, getting this thing, we just give it to the fabrication manufacturer. We call fab manufacturer. So they will manufacture the chip for you. And they are basically just chip productions. Like from the ingot, you get the slices, what we call blank wafers. Then there are process steps. Then patterned wafer. Then you get the dice. Red marks means some faulty. Eliminate them. Make bonding. And then again ship to the customers. So the basics, VLSI design basics are what we understand, CMOS design, CMOS gate design. So we have to understand basic principles or philosophy of the CMOS gate. And using the CMOS, what we are making the pass transistors, transmission gate, tri-state gate, some latches and flip-flops, some standard cell layouts, stick diagrams. Now, standard cell layout means some adder, subtractor, multiplier, or some other units, they would be designed and put as a cell. So when you will be writing the code, directly you can call them and put it over there. You don't have to design separately again. This thing is something like, when you write programs in C, you have some function. You call the functions. Listen. So similarly, so these cells, standard cells are also available. Okay? So you can use them in your design. So basically, metal oxide semiconductor. These transistors are the basic building block for any VLSI chip. So there are two types of MOS transistors. All of you know, NMOS and PMOS. But the obvious question is, why CMOS? Yes, we have the answer. CMOS contains both PMOS field effect transistors as well as NMOS field effect transistors. Now, PMOS drive a good logic 1, NMOS drives a good logic 0. Now, in the left-hand side at the top, the circuit has been given. It's a complementary CMOS circuit, which is basically an inverter. So if you give 1 at A, you will get 0 at the output Q, or vice versa. If you see the circuit, in the circuit there is no resistor, no capacitor, nothing, just two transistors. And at any time, only one of these two transistors will be on. Okay? Both the transistors cannot be on at the same time. So as a matter of fact, power dissipations will be very, very small, because entire circuit from VDD to VSS, you will see the current flowing. will be very small. Now, another thing, since the areas of these CMOS transistors are very small, then on a given area, silicon area, more number of transistors can be accommodated. Now, more number of transistors can be accommodated means indirectly it's very cost effective. So power dissipation is small, it is cost effective, area is small. So if we compare with BJT, then definitely it gives you the edge, and that's the reason. For VLSI circuits, CMOSs are used perfectly. Now getting all these things, understanding the fundamentals of VLSI and accepting the fact that CMOS is the basic building block, will go towards design of the processors. Now, basically here we mean processor, CPU, central processing unit of a computer. Widely there are two types of processors. There is a CISC, another is a RISC. CISC stands for Complex Instruction Set Computer, and RISC stands for Reduced Instruction Set Computer. From the name, you understand complex instruction set computer means the instruction sets are quite complex, very large, whereas reduced instruction set computer means the instruction sets are less and less complex. But doesn't mean that less powerful. Virtually they are more powerful than the traditional CISC processors. Some examples of the CISC processors are Intel X86, Pentium, Motorola 68000, NS320XX, AMD. So these are the processors. And RISC, Spark, MIPS, PowerPC, Acme Lavier, ARM processor, which is very popular today, PIC, and recently RISC-V has emerged. We'll discuss it later on. So, since today's lecture is centered towards RISC processor, but I feel that without understanding the CISC processor, it will be difficult to go for the RISC, because after all, the design philosophy for both RISC and CISC are very, very common. Very little differences are there from the design points of view. Okay, so first we'll go for the CISC, then we'll go for the RISC. So, yeah, am I audible?
Yes, sir, you are audible.
Okay. Okay. So, before going into the design of the CISC, let's have a look at what the computer is. Okay, even though all of you are aware of it, but just trying to recapitulate the whole thing. Basically, the purpose of the computer is to process the information, to store the information, and to communicate the information through input-output devices or through buses. So these are the three operations. So processing will be done by processors, storage will be done by memory, and communication will be done by buses or input-output devices. That's all. So these are basic building blocks. So CPU, at the right sides, the diagram, if you look at the CPU, memory, and I/O devices. So these are the three basic entities, and they are communicating through these buses. So when CPU wants to communicate with the memory, through address bus, data bus, and some control signals will be given. Same is the case for input-output devices. Now within CPU, arithmetic logic unit and control units, these are there. So operation of CPU is controlled by the control unit, and within the CPU there are separate units, arithmetic. We call it arithmetic and logic, but logic unit and arithmetic units are basically separate units, but put in the same building block. So basic components of the computer is data path. Data path performs arithmetic and logical operations. So it consists of what? Adders, multipliers, or shifters, like shift data in the left directions or shift data in the right directions, etc. Memory, it holds data and instructions. So memory is the area where instruction will be stored and where data will also be stored. Data could be written onto the memory, or data could be read from the memory. Okay. Instructions will be, once it is stored, it will be read one after one. And again, the memory could be, the fastest memory is the cache memory, main memory. Slowest is the disk memory, where larger amount of data can be stored. Okay. Cache is the smallest amount, and disk is the highest amount. Okay. So large amount of data will be stored in the disk, and they'll be brought to the main memory. So input and output, we understand. Control unit, it basically controls the enter operations of the computer system. So memories, if we just go by the hierarchy of the memory, the register is the fastest, then the cache, then the main memory, then the disk, then 10. So memories come in variety of speed, cost, and size. So register is the fastest. It is within the CPU. And if you go by the VLSI technology, on-chip access time is always faster than the off-chip access time. Okay, the main memory is kept outside the CPU. So to access the data from the main memory, access the data means to write the data or to read the data from the main memory. That will be definitely slower compared to the registers, because register is within the chip, same chip. Cache is the fastest. Now there are two levels of caches, level 1, level 2. These are used. Okay, so small amount of data is stored in the cache. So CPU will feel that always the data is there in the cache. So it will try to access the cache and it will execute the instructions from the cache. So as a matter of fact, it will be much faster. Disk is the slowest, in fact, because the bulk data will be stored on the disk, and it is basically non-volatile, whereas main memory is volatile. These days tapes are not used. Long time back it was used. Okay, is the slowest. So I'm not going into the details of this. So bits, bytes, and a simple processors, or you know that what is bit and what is byte. So this is a typical structure of a memory. Memory means what? A number of locations are there, and each location the data would be stored. And the size of the memory is always power of 2. Hence 2 to the power 2 means there are 4 locations, 2 to the power 3, 8 locations, 2 to the power 10 means 1024 or 1K locations, 2 to the 21 meg. And word size, it could be 8-bit or 16-bit or 32-bit or 64-bit. So if we say 2 to the power m into n-bit word, that means 2 to the power m locations, and each location consists of n bits. So this is address space at. So memory will have a read signal, a write signal, and some address lines. Address lines will tell from which locations the data will be accessed, whether the data will be written or data will be read from. And data lines, n-bit data lines, these are functional because they can be written onto it or data can be read from. Address line is unidirectional because address is given to the memory. Okay. So if there are 2-bit address lines, for an example, so address lines are 0001, 1011. And in each locations, that's 8-bit or 16-bit data is stored. That data will be available on the data bus depending on what operation you want to perform, read or write. Typically, these are read bar or write bar. Since we deal with the MOS transistors and basic MOS transistors, they operate in the complementary form because CMOS. So that's why we use in the CPU, you will find read bar, write bar, etc. Not read, write. Otherwise, again, you will have to use extra logics, which is not required. Okay. So 16 bit means 2 to the 16, that many words. 20 bits means 2 to the 20. 2 to the 20 means 10 to the 6 words. So computer technology trends, if we go by the technological trends, we'll find that after every 18 months, basically number of transistors in a processor, it's double. That is 60% increase in year. But today, in fact, even the Moore's law is not that valid because the rate of development has got changed. So now let's come to the introductions to basic architecture of a CPU. So what do you mean by the architecture? Basically, it's the design of computer at the hardware-software interface. Okay. So that means we have to design some instruction set. And according to the instruction set, the hardware will be architect. And by the instruction set, that processor would be programmed. So it's basically the hardware and software interface. So that means we need to understand the instruction set design, because based on the instruction, the hardware design will be made. And then we have to understand computer hardware design. The instruction set design of a computer includes anything a programmer would need to know to make the computer run correctly. Okay, so instruction set design, I believe that most of you will be aware of assembly language instructions. Okay. I'm sure that you must have gone through Intel 8085 microprocessor. And 8085 has the instruction sets. So if you want to write a small program, what we'll be doing out of the instruction set, we'll choose the instructions according to a particular program and write using them. And when you write the instruction set, you have to understand. So you have to understand the internal architecture of the CPU. Internal architecture means how many registers the CPU has. Out of that, how many are general purpose registers? How many are special purpose registers? What are the instruction sets? What operations can be performed? What is the format of the instructions? Okay. Addressing mode, exception handling, means the interrupts and all. I'm just giving a small example of Intel 8085 since I'm sure that all of you are familiar with Intel 8085 microprocessors. Okay. Like it has a number of instructions, less than 200, I think. It has different addressing mode, like direct addressing, indirect addressing mode. Okay. Then register addressing mode, etc. Instruction format means how they are specified. There are some instructions are of 1 byte, some of them are 2 bytes, some of them are 3 bytes. Like load accumulate array with some address is a 3 byte instructions, whereas load immediate with some data is a 2 byte instructions. So these are the instruction format. Like it has a number of interrupts, like hardware interrupt, like INTR, or trap, or RST 5.5, RST 6.5. So they're the interrupt lines. Like if a signal comes over there, how the CPU will react to it. So these are basically, in fact, when you design the instruction set, all these things have to be kept in mind. We'll discuss all these things when you go for detailed architecture. So hardware design determines the implementation of the various computer components. From the instruction set, the requirement will be coming. For an example, you have an add instruction. That means definitely an ALU will be required where some adder will be there. or if there is a multiplication instructions, multiply two numbers, then some multiplier should be there. Or if there is an instruction to shift the data, then shifter should be there. So etc. And basically there are two buses, data bus and address bus. Data bus gives the data for a given address. Okay, and some control signals are there, which will be controlling the entire operations. So in order to simplify the task of computer, we use the level of abstractions. Okay. So before just going into the architecture of the CISC, let's go through certain terms. A clock cycle. Okay, CPU operating on a clock. So for an example, the clock rate is 200 megahertz. Then what is the clock cycle time? 1 by 200. This 5 nanoseconds. So if a computer has a clock rate of, let's say, 100 megahertz and requires 200 clock cycles to run a given program, then the execution time you can easily find out. What is the total CPU execution time? Or let's say you have a number of instructions. For each instruction, you know the execution time. So you add them total and divide by that. You will get average execution time. CPI stands for clocks per instructions. So per instruction, how many clocks are required? Okay. For RISC CPU, this CPI is 1. That means in one clock cycle, one instruction will be executed. Now, other performance matrices are MIPS or MFLOPS. MIPS stands for million instructions per second. As the speed of the computers are getting enhanced, okay, clock frequencies are going higher and higher. So now it is more convenient to describe the performance of the CPU in terms of MIPS, means million instructions per second. So per second, how many millions instructions can be executed? That is MIPS. MFLOPS, some CPUs are having floating point operations. Okay, so MFLOP stands for million floating point operation per second. Okay, so MIPS is a million instructions per second, and MIPS million floating point operations per second. So these are also some performance metrics for the CPU. So now let's go to the instruction set design in detail. So now what you understand, for designing a CPU, before designing the hardware design of the CPU, we must have to go through the instruction set design, which is very, very important. Typically, this term is known as ISA. It's a very common term today in the computer world. The instruction set architecture, ISA, is the interface between the hardware and the lowest level of software. Because these instructions are written in the assembly level language, which is very close to the machine. Now, if we talk about the programming language, high level languages are like C, C++, or Java, or Python. So they are high level language. So to write programs in these languages, you don't need to know the anatomy of the CPU. Anatomy of the CPU means the CPU internal structures and all. So a person who will be writing the program in high-level language doesn't need to know the internal architecture of the CPU. Or in other words, they don't need to be a computer engineer. So programmer of a computer can be from any discipline. Okay, like to drive a motor car, you doesn't need to be a mechanical engineer. Same is the case over here. Wherever computer doesn't understand these high-level languages, computer understands it's only machine-level language, at the lowest level of language. So, but to understand this lowest level of language, you need to know the internal architecture, means how many registers are there, okay? What are the instructions, all these things. So this lowest level of software is that, and depending on the lowest level of software, your hardware architectures will be built. Okay. Now, having said that, now you have to understand what are the different types of computer architecture. Now, broadly, you can classify von Neumann architecture and Harvard architecture. Von Neumann architecture, here instructions and data are stored in the same memory. There is no demarcations. Instruction means basically program, which is sequence of instructions that will be stored in the memory, and data will also be stored in the same memory. So it allows a single memory interface and improves storage utilizations. It will be cost effective. So Harvard architecture, which was conceived in the University of Harvard, Harvard University. So their philosophy is data and instructions are stored in separate memories. Data will be stored in a separate memory and instructions will be stored in a separate memory. Now, what is the advantage? The advantage is the memory bandwidth utilizations will be very high, in fact. The bandwidth, why? Because program and data, if they are stored in the different memory, for an example, if we require the data and program to be faced at the same time, there will be a clash in the von Neumann architecture. You have to give priority either to instruction or to data. Whereas in the Harvard architecture, they are totally separate. So that will be much faster. But this fastness, what you are achieving at a cost. So now there is a trade-off, whether you will go for von Neumann architecture or you will go for Harvard architecture. Okay? But Harvard architecture concepts are becoming common in most of the RISC processor architecture. Now, issues in the instruction set design. So, after having these discussions, certain points will definitely come to our mind. What operations to be performed by the instructions? That means what will be the instructions? Now, to get the answer of these questions, you have to think of categorizations of instructions. What are the different categories of instructions that you have to think of? Then, how many operands to be specified? Operands means the data or some information related to data. How many registers are involved and what they are? Which functional units will be involved? Functional units means if it's an addition, then adder will be involved. If it's a shifting operation, shifter will be involved. So on. How to encode using consistent instruction format. That means what should be the structure of the instruction? In one word, that is the thing. So these 5 points are very important. What are the different types of instruction? Okay, what are the different functional units will be involved? And what is the instruction format? Now first let's see the instructions. Each instruction consists of how many steps? Okay, there are a sequence of steps involved for executing each instructions. Broadly, there are 5 sequential steps. Well, this thing is vary. In fact, there are architecture instead of 5, they take 4, so on. But basic essence is the same. First, the instructions. When you deal with the von Neumann architecture, is basically a store and forward concepts. Now, first the instructions are stored in the memory. From the memory, instruction needs to be fetched onto the CPU. So CPU and memory. So there must be an interface between CPU and memory. Okay. So through the interface, from the memory, the instruction should be brought to the CPU. So, after the instruction is brought to the CPU, it needs to be decoded. Decoded means what is the instruction? What is the meaning of the instructions? because the action has to be taken accordingly. So instruction decode determines the required action. Then operand fetch, it may show happen that this instruction needs some operands. Okay, like let's say add a register within the CPU with some memory locations. Means the data in the memory locations need to be fetched, that is called operand fetch. But it is not compulsory for all the instructions. After getting the data, the instruction needs to be executed. After executions, the data, the result needs to be written back. I'm just giving an example. Let's say add R1, R2, R3. R1, R2, R3. These are instructions. Say R2 and R3 are two registers. They will be added and the result will be stored into R1. So first instruction needs to be fetched. Second, it needs to be decoded. And after decoding, it is found that it is an add instruction. Then what has to be done? The contents of R2 and R3 should be brought to the arithmetic and logic unit. Then execution, that means arithmetic operation will be performed. After the operation is complete, then the result will be stored to R1. So that is a write back operation. So these are the 5 cycles for each instruction. So now, instruction set design. What should be specified in the instruction? What is the format of the instruction? Then data type, data size, what operation to be performed, etc. Now, instead of going into the details of this, we'll straightway go to the types of instructions. So first thing is that, let's assume that our intention is to design an instructions for a CPU. Now, first thing, the specification has to be given, like what is the data type, what is the data size, etc. Then what should be the instructions? Let's say we are designing only the instructions right now. So different like data transfer must be there. We are dividing the total instructions into a number of subgroups. So data transfer means storing the data from CPU to memory or memory to CPU, or within the CPU there are some registers. Transfer will be within the CPU from one register to another register, etc. These are called data transfer. Arithmetic instructions could be either integer or floating point operations like add, sub, multiplications, divisions. Logical operations like AND, OR, NOT, XOR, etc. Or data manipulations like shift left, shift right, rotate left, right. Then transfer of control like jump instruction. These are called branch kind of instructions. Branches, there are 2 types of branches, conditional branch and unconditional branch. Okay. Conditional branches are like jump on carry, jump on equal to, etc. Then subroutine, like function call, so call, return. And the machine, there must be some means to stop them. It's called machine control. These are halt instructions. Then some interrupt instructions will be there, like trap or return from interrupt, etc. So, although there are many different types of instructions, but frequently used instructions are load, store, or add, stop, and or not, compare, branch, move, call, return. So these are the most common instructions out of all this. Now, what are the different components for designing a CPU? Where slowly we are going towards designing a CPU. Within the CPU, there must be some registers for transferring the data. Like if we just look at the instructions, say data transfer instructions, that means loading the data into some registers, or storing the contents of registers, or transferring the data among the registers. So these are the different type of data transfer. So for that, what hardware we require? We require a register. Now register consists of what? A number of flip-flops. And flip-flop is what? Is basically we can view that is a 1-bit memory shell for storing 1 bit of information. So register is basically a group of flip-flops. So n-bit register means n number of flip-flops. Okay. And then registers, shift registers is a kind of serial registers will be connected and data can be transferred serially. So here in fact, so the concept to hardware. So whatever we have discussed so far, we understood that we need registers, and for registers we need flip-flop, and basic flip-flop, how the flip-flop can be designed. Now there are two concepts. Traditionally, we have learned that 4 NAND gates will be connected like this fashion, what is given in the bottom of this diagram, Q1. Now 4 transistors, 4 NAND gates and 1 NOT gates. That gives a complete D flip-flop. Now, as far as the number of transistors are concerned, because when we are ultimately going for the VLSI design, we are very much concerned about the area. We'll always try to minimize the number of transistors. Now here, for VLSI, each NAND gate will consist of 4 number of transistors. So here, how many transistors will be required? 4 into 4, 16, and NOT gate will consist of 2 transistors, 18 number of transistors. Now let's look at whether we can design the same thing using some other concepts. At the top, let's look at the third diagram. One is the mux, and there are 2 transistors, 2 NOT gates, a clock and D. Let's say it is a rising edge triggered flip-flop. So when the clock is going high, then whatever is there in the D, that will be at the output of the mux. This clock is connected to the select line of the mux. Let's say when it is 1, the upper input will go to the output, and when it is 0, then lower input will go to the output. And these NOT gates are connected back to it. Interestingly, so let's say D, I want to store 1. So we'll give 1 at the D input. So when the clock is going high, then what will happen? This 1 will be passed on to the output of the mux. Then Q bar will be what? 0. And 0 output will be of the second NOT gate will be 1. And now clock has gone 0. So this output will be there. So 1 is being stored. So in that way, continuously, in fact, whatever data you have given, unless you change it, that data is getting stored. How many transistors are required here? 2 to 4, and 1 disk gate. Mux needs only 2 transistors. Look, this is the circuit of the mux here. Just by giving the select lines. So 1/3 of the number of transistors will be required for making this D latch, and that's what these are done in the VLSI chip instead of the traditional way of designing. So one thing we must remember that when you do the innovations, there are different ways, especially in this technology in VLSI. One is the device improvement, that is the technology improvement, and technology is how to improve this size, like reduce the sizes of the transistors. Okay. Another is the architectural development, how using these gates or making some tricks in the architecture sides to reduce the overall number of gates. Okay, so this is the here in fact we are using that. Okay, so problem of register is solved now. So using register means the fundamental units of the register is the flip-flop. And flip-flop is made in this way. And putting a number of flip-flops, we can make the register. Then comes the tri-state buffer. Now here, the tri-state buffer you can make by only one transistor. You consider here one NMOS transistors. Now in the gate, if you give 0, then what will be the output? If I consider that one transistor is there, okay, NMOS, input is Z and output is Y, and select line is the gate, enable line is the gate. So if gate is 0, then there won't be any connections between Z and Y. This is open. That means it's a tri-state. But if your gate is 1, then the switch will be on, transistor will be on. Then whatever you give at Z, you will get at Y. Isn't it? So this is a tri-state buffer. This is a tri-state buffer, logical form. Here, when enable is 0, the output is floating. And when enable is 1, then whatever you give at the input, you will get at the output. So symbolically, one is the enable line, one is the data in, one is the data out. So that is the tri-state buffer. This is the register with data parallel loading. So 4 flip-flops. You give data at the input sides, B0, B1, B2, B3 parallelly. So that data will be stored within that at the rising edge of the clock. The rising edge can be made by you clock and differentiate the clock. Then you will get the rising edge. And differentiator can be done by RC circuit, simple. So you take a high pass RC circuit, C and then R. Input you give the clock. So output will be in fact the differentiated form. So that will give you the edge. And at this edge, the data what you are giving at the input will be loaded or will be stored. And same data, if you want to get, you can get it from Q0, Q1, Q2, Q3. These are the output lines. So in the output lines, what you can do, you can give the tri-state buffer. So when the tri-state buffers are enabled, then only you will get the data. Similarly, at the input side also, you can give the tri-state buffer. So when this is on, only then the data will be stored over there. So some read-write logic you can give here so that when input enable is there, then the data will go to the input sides. When the output enable is given, here they have written only enable, we can write the read signal. So when read is 1, then the data will be available at Q0, Q1, Q2, Q3. Now tri-state buffer. Using this tri-state buffer, the data can be transferred from one register to another registers. You assume that there is a bus. Bus means a number of lines. Okay. So data in, let's say data in is coming from one register 0. Okay. Here I have shown only one tri-state buffer. So if the register is 8-bit, there will be some 8 tri-state buffer will be there. So when enable 0 is there, that means data will be available on the bus. And when enable, let's say 4 is 1, that means that data will be entered into the register 4. So if you want to transfer data from register 0 to register 4, then for register 0, you make enable, that is you call it output enable. And here you make it input enable of the concerned registers. So data will be automatically stored into that register. Okay. So it's basically, this is in the right hand side, if you see the diagram, that gives you the bidirectional lines. So there are 2 buffers, they have been connected like that, and giving the enable signals. Data will go from input to output or vice versa. So you can make the multiplexers using tri-state buffer. So these are the tri-state buffer. Okay, A0, B0, C0, and D0. And all the outputs are connected together. Now let's say select. since there are 4, A0, B0, C0, and D0, you will be requiring 2 lines, S0 and H1. So depending on S0 and H1, 0, 0, 0, 1, 1, 0, and 1, 1. So one of them will be selected, and that input will go to the output. So is it not a multiplexer? This is another way of designing a multiplexer using simple tri-state buffer. Okay. Like at any time, only one of the tri-state buffer will be enabled. Okay. So since, let's say when A0, input A0, that is selected, that means 0 line will be high, 0 line of the decoder will be high, rest of them will be low. So rest of them will be low means what? Their output will be hanging, will be tri-stated, only A0 will be available. So in that way, you can select any one of the input. So these are MUX circuits. And tri-state buffer easily you can make by only one transistor. Gate will be forming the select lines, like enable lines, and drain and source can be interchanged as input or output line. So now you understand how these MOS transistors has made the things much simpler. So these some serial registers. Each time you give a clock, then what happens? The data what was there in D3 will be shifted to D2 and so on. So already we have discussed about the memory. Memory has address lines and data lines. Data lines will be bidirectional. Some chip select line and read bar and write bar signals. There are two nomenclature like Motorola concepts. They use one line, read write bar. That means either it will be read or write. Whereas in Intel concepts, read bar and write bar, there are two separate lines. When read bar is low and write bar is high, that means it's the read operations. And when write bar is low and read bar is high, means it's the write operations. And when read bar, write bar, both of them are high, that means neither read nor write. And definitely read bar and write bar cannot be low at the same time because read and write cannot be done simultaneously for this kind of memory. However, there are another type of memory, these are called dual port memory, where the data can be accessed from memory by two processors simultaneously, except the same locations. Anyway, we are dealing with this normal memory, where at a time only either read or write operation can be performed. Okay. So for Intel, read bar and write bar, two separate lines. So drawback is one extra chip, extra line will be required, extra pin will be required. But there is an option that neither read nor write. This also can be possible. So extra power dissipations will not be there. Whether when you are making it either read write bar, so either it will be read mode or write mode always, which is not desirable. And there are different types of memory, like RAM, static memory, dynamic memory, and there are non-volatile memory like flash memory, EEPROM, EEPROM, OTP-ROM. OTP means one-time program. Only one time you can program. Or mass programmed ROM. At the time of manufacturing the chip, you tell what are the data to be stored. They will be there, but you can't alter it. OTP, only one time you can program, not next time. But EEPROM or EEPROM, they can be programmed a number of times. Okay, you can erase, you can program, and the advantage of EEPROM is within the circuit you can insert data onto that. You don't have to clean the memory from the card. Whereas EEPROM, erasable programmable memory, it cannot be possible to program it within that. First, you have to erase it. For erasing, you have to bring it out from the circuit and put it under ultraviolet lamp, erase it, and then again put it onto the circuit. So this is a lot of hazards are there. Whereas EEPROM, keeping it within the circuit, you can program it and erase it. And there are different types of DRAMs, like asynchronous DRAMs, synchronous DRAMs, double data rate SDRAMs, okay, for faster performance. Then Rambus DRAM provides very high data transfer rate, and then cache DRAM is the fastest. So there are 5 types of DRAMs. SRAM and DRAM, if we just differentiate, SRAMs are faster than DRAMs, but capacity will be much higher in DRAMs because DRAM consists of only one capacitors. So this is the basic structure of the RAM cells. As I've shown you earlier, that two not get connected back to back forms a flip-flop. And these are tri-state buffer. So let's say you give one data, want to store one. So through this line, bit line, you give one data, and that data one, let's say if you want to store one output will be 0, that 0 will come here in the next one. So this one will be stored unless you want to change it. If you want to read the data, you can again read the data because the lines are bidirectional lines. And these are the basic structures. Because NOT gates means one complementary MOS. You connect them in that way, back to back. And in the lower sides, the circuits of DRAMs, only one capacitor is there. So complexity is much less compared to static RAM. And since the complexity is much less, what you can do in a given silicon area, more number of bits can be there. Okay. So here, if you want to store a data in a DRAM, in the data line, that means in the drain, you give the data, and write, means you are writing the data that you keep in the gate. So the transistor will be enabled. Once it is on, that data will be stored onto the capacitor. And similarly, on the capacitor, you can take the output. You can read the data as well. Okay. So simple is that, is DRAM. Hello? Is there any problem in?
Hello, sir.
Yeah, am I audible?
Yes, sir. You are audible.
Okay. Because some noise was coming.
Yes, sir, audible.
Okay. So this is the DRAM. So if you compare with the static RAM and DRAM, here what you're finding? 1, 2, 3, 4, 6 transistors and replaced by a single 1 transistors and 1 capacitors. So efficiency in the area is more than 1/3 times. And in fact, organizing this properly, like selecting the address. If there are, for the simplicity, let's say there are 64 rows. 64 rows means you will be requiring 6-bit address lines. 6-bit means 2 to the power 6 equal to 64. One of the lines will be selected. So address decoder will select one of the lines. And in that line, you can store the data to bidirectional line. So if the write enable is there, then the control logic, you enable the control logic in such a fashion, such that the data will be stored. Or if you want to read the data, output enable, that is the read. Output enable is nothing but the read signal. If you give that thing, then whatever the data is there, that data will be available at the input-output line. So IO0, IO7, this is input-output lines. Through same lines, either you can write the data or you can read the data by changing, controlling these signals. OE, write bar, CS. CS is the chip select. For any operations, whether read or write, to be performed, chip select line needs to be high. Okay, so that is the basic memory design. The memory consists of what? Some address decoder, some cell. So if you want to design a 64 into 4-bit RAM, 64 into 4-bit means 64 locations, and in each locations there will be 4 bit. So number of transistors will be 64 into 4. And number of memory cell will be that. And corresponding to each memory cell, how many transistors, you know that already I have discussed. So you select a particular row and read the data or write the data onto the particular row by this logic. So this is simple, this is the memory design. So once you do this entire design, then write a Verilog or VHDL code and do that. You can jolly well test it. In fact, using Xilinx software, write the Verilog code and test it and simulate it. That is quite possible. Just at home, you can do design and test it. And memory hierarchy already I have discussed, So processor, within the processor registers, the first is memory, then the cache, then the main memory, then the disk. So this is the memory hierarchy. Okay. Now we'll go for designing the processors, understanding the memory and what are the registers how the data can be transferred. We're slowly going towards designing an advanced processor. Now, when you design a processor, definitely one angle is from the computer science point of view, but ultimately the chip has to be manufactured. So you must have to look at the electronics. Okay? So basic parameter of the electronics and what are the requirements in the market and what are the basic need of the programmers. So keeping all these things in view, there are certain parameters. One is definitely the chip, the cost should be very low. That is the most important thing. Speed has to be very high, what we call high performance. Okay. Then power consumption should be very low. And it should be flexible. So whatever I have designed today, I would be able to augment that design if we want to change in the upward directions. So that is called flexibility. So design means ultimately we are writing the code. So that code should not be wasted. The same code, just by adding something, it will be upgradable. And it should be scalable also. Okay. So these are the factors we have to consider in mind. So there are different type of configurations like IntelliFushi, there are port socket configurations. Like from one CPU, you can make 4 CPU on the same chip. So this will be helpful for parallel processing, such that all 4 CPUs can work concurrently. That means if we just divide the program into 4 modules and each CPU does the task of each module and they communicate among themselves, it will be much more faster. So first, before going into the RISC architecture, now we are ready for designing the CISC processor. So as we know that CISC stands for Complex Instruction Set Computer. Here the number of instructions are very large and complex, like your Pentium or DEC, this kind of computer systems. So there are various types of instructions, large variety of instructions, rather, large and complex instruction addressing modes. Number of general purpose registers are less. That means data will be stored mostly on the memory. Memory may be segmented. Architecture could be pipelined or non-pipelined. I have not yet discussed pipelining. We'll discuss soon. Variable length instructions means instructions lengths are not fixed. Some of the instructions are of 1 byte, some of them are of 2 byte, some of them are of 3 bytes, etc. And program and data reside in the same memory bank. And they're basically based on microprogram control unit. Now, instead of telling all these things in nutshell, what we can say that complex instruction set, number of instructions are large and complex. That is number one. They are basically von Neumann based architecture. So program and data reside on the same memory. Control unit is designed using microprogram control unit. And number of registers are smaller. Addressing modes are also quite complex. So, to understand the RISC architecture or to understand how to design a CISC computer first, let's take an example. Now, for the sake of understanding, let's take a smaller example. If we understand this small example, to augment it to a bigger one is not difficult at all, because same design philosophy will be applicable. So, from the designer's angle, a designer will be requiring the specifications. So first specification is, what is the instruction format? Let's say the instruction is 12-bit. That's the format. And all the instructions are of same length. Let's assume that. And 12-bit instruction means the instructions will be stored in 12-bit form in the memory. Okay. So from this point, automatically you can say that memory size will be 12-bit and 4-bit opcode and 8 bits are operands. Okay. So 0 to 7 means 8 bits, therefore operand. Operand means basically address, and opcode is 7 to 11 means 4-bit, 8 to 11, 4 bits. So using 4-bit opcodes, how many instructions are possible? 2 to the power 4 equal to 16. Using 8-bit operands, how many address lines? Only 8-bit address lines means 256 locations. So easily from this instruction format, we can view what is the memory structure. So memory will be, address lines will be 8-bit and each location will be 12-bit. 8-bit address lines means total locations 2 to the power 8 equal to 256. So memory is 256 multiplied by 12. In that way, we just define the size of the memory. Okay, like for a room, we say this length and breadth. The memory also, like how many locations multiplied by what is the size of each location. Now, since our opcode is of 4-bit, we have only 16 instructions. 16 instructions how to choose. So first we have to select what are the types of instructions. Now here let's assume that we have data transfer instructions, that has to be there, then arithmetic instructions, then branch instructions, then subroutine instructions, and machine control. So 5 types of instructions. And within that, all 16 instructions need to be accommodated. So data transfer is load A with some address. So there is a register called accumulator where the data will be loaded from the address of the memory. So load A address. What is the counterpart of load A? Is store A. So this is direct addressing. There is indirect addressing, like there is immediate addressing, like load immediate data. So data will be directly loaded onto the accumulator. Then the add, sub, then XOR, and jump. Jump to address means it will go to that address. Then jump carry, jump on 0, call. If there is a call instruction, there must be return instructions. Then load stack pointer. So to form the call, the stack pointer will be required because call means call and jump. The difference is for call instructions, the flow of program will be sent after the return instructions. So call address means it will go to a specific subroutine given by this address. Once that subroutine task is over, there must be a return instructions, and return will return you to where the call was taken. Let's say the call was taken when the location program counter locations was X. So X plus 1 would have been the next instruction to be executed. But since it's a call, it will go to that address. But once it is over, it will come to X plus 1. That's the thing. Now from these instructions, what do you understand? We understand that there must be an accumulator at least. There must be some adder. There must be some logic unit which can perform XOR or AND, etc. So let's try to divide the total number of registers into some category. In any CPU, when you design, there are 2 types of registers. One is the general purpose register, another is the special purpose registers. Now, general purpose registers are those registers where data will be stored. And special purpose registers are those registers which will be used by the processor itself. Normally, user doesn't have any access to those registers. So here, so far, we find that accumulator is one general purpose register. Now, since the CPU will execute the instructions one after one, that means there must be some counter which will keep track of the current address of the instructions, and this is known as a program counter. So it's a counter which keeps track of the address of the current instructions. Okay. So this is a special purpose. So program counter is one register which will be required. Another is the instruction registers. When the instruction is fetched from the memory, it must have to be stored somewhere within the CPU. So this register will be instruction registers. Now what should be the size of instruction registers? Is equal to the size of the instruction, because instruction will be stored in the instruction registers after it is being fetched from the memory. Now what is the size of the instruction? Is 12-bit. Already we have discussed from this diagram. We can get to know. So instruction register size will be of 12 bits. What is the size of program counter? It holds the address. What is the size of the address? Is 8-bit. The program counter will be of 8-bit. That's all. Now, then accumulator will hold the data. Data is 12-bit. So accumulator size will be 12-bit. Then here another register is there, stack pointer. Stack pointer is what? Stack pointer is basically, it holds the address. It is 8-bit. Okay. And X is in indirect address registers. So again, X register size will be 8-bit. Load X means load accumulator with the contents of X registers. So contents of X register will be the address. So use that address, get the data from the memory using that address, and that will be coming to the accumulator. So that's why it's called indirect addressing mode. So here, how many addressing modes have been used here? Direct, indirect, immediate. That's all. On stack pointer is there. Just remember that whenever there is a call instruction, there must be a stack pointer. Okay? Because the return address will be stored on the stack. Stack is any part of the memory and pointed by the stack pointer. So the difference between jump instruction and call instruction is, for a jump instruction, it cannot come back. But for call instruction, after finishing the subroutine, it will come back to the original positions from where call was taken. So basically, my intention of giving the instruction is, from the instructions now, we can understand how many registers will be used. And based on that, now we will draw the schematic. So immediately I can draw the schematic. Now this schematic has come from the instruction set, mind that. So first, as I said, that program counter will be there. So program counter is what? It points the addresses, points to the memory for taking the current instruction. So what should be the size? 8-bit address. Now memory and program counter, to avoid the direct communications, there must be a buffer. That buffer is MAR. MAR stands for memory address registers. Okay. So PC will give its contents to MAR. How? PC content will go to MAR. There are a number of control signals at the top of each registers. I and V. I means input enable and V means output enable. So when output enable is high, contents of PC will be placed on the bus, and I of MAR is high, that data will go to MAR. So to transfer data from PC to MAR, or to MAR, it's called register transfer language. So contents of PC will go to MAR. For that, all that we have to do, output of PC should be enable and input of MAR should be enabled. So OE should be high and I should be high at the same time, and data will be transferred. So that directly goes to the memory. Now, to get the contents of memory, read bar signal has to be made low. So memory contents will be placed onto the bus, and wherever it goes, that should be made enable. For an example, let's say we want the contents of memory to go to the accumulator. Okay. Yeah, so this accumulator should be input enable and memory output enable, read bar So contents of memory will go to the register. So in that way, the flow of information is maintained within the CPU. So to design this CPU, now from the instruction set architecture, you can easily make this schematic. So what you require? First put the special purpose registers like program counter, instruction registers over here. Memory is outside the CPU, mind that. Now program counter, there must be a bus. So the rule of making the architecture is draw the bus. So this bus size is what? 12 bits. Okay, which includes the total instructions. And this 8-bit will be your least significant 8 bits are connected. Okay, from the bus. Bus is 12-bit. Out of that, you extract the least significant 8 bits. So PC, MAR, then instruction registers, all of them are connected. Then instruction registers will be connected to the instruction decoder. Which part? The 4 most significant bits of the instruction register goes to the instruction decoder. So decoder output will be 16, depending on the 4-bit opcode, and that will go to the control unit. Control unit will generate all the signals. Now X is what? Indirect address registers, that is 8 bits. Then you have to have a ALU. One is the accumulator. Accumulator input will go to the ALU. Another is from the temporary register, because to do any arithmetic operations like addition, subtractions, you need to have 2 operands. So one will be held by the accumulator. Another is another registers will be requiring, that is temporary registers. This now, based on the arithmetic and logical operations, some flag register contents will be set or reset. Now here, how many flag registers will be there? How many flag flip-flops will be there? That depends on your conditional branch instruction. So here, jump carry, jump 0. So there will be 2 flag registers, 2-bit flag registers. Okay. So draw the schematic and put all the control signals. Now how to put the control signal? PC. So it is a bidirectional. Like contents of PC can go, or PC can be changed for jump instructions. Jump to this. Let's say jump to F2. That F2 will go to PC. So PC is bidirectional. It will have IE and OE both. All these registers or ALU will have some clock that is common. So the operations will be synchronized with the clock. So IE and OE you just put, and PC should be incremented after every clock cycle. So there is one INCR signals. Initially it has to be reset. As when you start the computer operations, don't you have the hard reset? Means it starts from the 0 locations. So your design is very simple, you know. So from the instruction set, just directly map it onto architecture. So what we say, mapping the instructions onto hardware. That's the reason we discuss about hardware-software interface at the lowest level. So lowest level of instructions, based on that, we are making the hardware architecture. So rule is, first design the instructions. And instructions will be designing based on what? Based on the specifications. So what is the specification? First, determine what is the size of each instruction. Out of that, what should be the number of instructions? So if there are 16 number of instructions, 4-bit opcode will be required. If there are 32 number of instructions, there will be 5 bits. So in that way, you define operand size. Based on that, your memory size will be determined. So instruction set architecture, that's the most important in the CPU design. And this instruction set architecture, what we are talking about, this depends on the requirement. Okay, whether it will be high-end processors or low-end processors or the processor for low-end embedded applications. So based on that, the VLSI design engineers, they make this CPU. Okay, so here I have taken a small examples just for understanding. So easily we can expand it to, instead of 12-bit, it can be made 32-bit. There could be a large number of registers, but the basic concepts are the same. Now the thing, we have to design the control unit. That means how these control signals will be generated at different times. at. For that, there is a technique. So we call it micro operations. Just I'm giving you one example to understand these micro operations. Now, for executing each instruction, a number of clock cycles are required. It's not happening in just one clock cycle, everything is happening. Say, we want to add some address. Meaning is, add the contents of accumulator with the memory address given in the instructions. And after addition, the data will be stored in the accumulator. So it cannot be done in a single cycle. A number of operations need to be done. Already we have discussed the total instruction execution can be divided into a in terms of number of clock cycles, like fetch, then decode, operand fetch, execution, and write back. So same thing will happen over here. So in each clock cycle, what happens we have to see. Fetch cycle is common for all the instructions. Rest of the things will be different. So here the fetch cycle, if you see, that first PC contents will go to MAR. Fetch means what? From memory, the instruction has to be fetched onto instruction registers. For doing that, first PC will give the address to MAR. Then, getting the address, memory will give its contents to instruction registers. So at T1, what happens? T1, PC goes to MAR. We just see the third column here, micro operations. So T states are written in the second column. In the first column, what is the instruction? Fetch is not an instruction, but I have written here to understand, because the fetch will be common for all the instructions. So at T1 cycle, what happens? PC contents goes to MAR. Then at T2 cycles, what will happen? Memory contents will go to instruction registers. So memory pointed by MAR will go to instruction registers. Let's see. Exactly that is there. Memory pointed by MAR goes to instruction registers. And at the same time, PC should be incremented by 1 for fetching the next instruction when its turn will come. Now, to increment PC, it doesn't affect the bus. So that's why both the things have been done concurrently. Again, NAR goes to IR, that means memory content goes to IR, and at the same time, PC is incremented by 1. Otherwise, it could have taken another clock cycle. So it's a wastage of time. Since our intention is to make a faster processor, we'll try as many as parallel micro operations could be done. Then, after that, so at the end of second clock cycles, the instruction is directly gone to instruction register, and the 4-bit most significant bit has gone to instruction decoder, and assume that instruction has been decoded. So once it has been decoded means it is understood what has to be done. So let's say the instruction is load accumulator. Let's say load accumulator with address. So load accumulator with address, what will happen? Now again, memory has to be given the address. That address is there in the instruction register. Because when the instruction was fetched to instruction registers, there are two parts. One is the instruction opcode, another is the address. Now this address will again go to the MAR. Then MAR will point to the memory. Then memory will send these contents to accumulator. So 2 more clock cycles will be required. Here exactly. At T3 cycles, instruction registers, the operand 0 to 7 means 8-bit address is going to MAR. Next cycle, contents of memory pointed by MAR goes to accumulator. That's all. Now what has to be done? Go to T1. Means now again it will go to the next fetch cycle for fetching the next instruction that is written by go to T1. So in that way, we can write the micro operations for all the instructions. Is possible? Now, out of that, once we write the micro operations, we find what is the maximum number of T states required. So here we are finding that T6. So 6 number of T states will be generated, will be required. So in general, hardware control unit, we see the block diagram. So intention of hardware control unit is to generate the control signals. Now what are the control signals? These all are the control signals like IE, OE, INCR, IE of NAR, or OE of instruction registers, etc. are the control signals. Now, if you see it carefully, corresponding to each micro operations in the columns, there are some control signals, different control signals. Some of them will be 1 or 2. In most of the cases, you will find not more than 2 control signals will be activated at a time. Means one register content is going to another register. So for that, output should be enabled for that register and input should be enabled for that register. Or for addition, subtraction instructions, similar thing will happen. So these are the control signals. So our intention is CPU design means basically now to generate the control signals. Okay, the rest of the things will be there. So this is the block diagram. This is a control signal generator, which is generating the control signal. What are the inputs? One input is the instructions from the instruction decoder. Let's say 4-bit opcode. So how many? INS1, INS2. It will be up to INS 16. So 16 instructions. And time. T1, T2, T3, T4, T5. These are the time. And some condition code signals. Now time. Why the time is required? Have you noticed one thing? Let's consider first here T3, okay, and instruction is some, let's assume that sub instruction SUB and time is T3, MAR is 1, IE MAR is 1. So you find out IER MAR is 1 for which cases? Number 1 case we find if the time is T3 and instruction is sub, then IEMR is 1. Also, told you go below. If the instruction is XOR and time is T3, then also it is 1. Again, here also, if the instruction is AND and time is T3, it is 1. So we can form a Boolean expressions. So IEMR equal to SUB into T3 or XOR into T3 or AND into T3. So this logic easily we can form. So this in that way we can form the logical expressions for all the control signals. So this control unit generator, it first get the T states, T1, T2, T3, T4, depending on that, and instructions, and what is the condition code. Condition code is required for some jump instructions and all. It will generate the control signals. So the block diagram is very simple. Within the block diagram, some logic gates will be there. And this, how to get these Boolean expressions? From this table. So basic intention is to write the micro operations for each instructions, form this table, write this control signal, so it will be 1 or 0, and from that you generate the Boolean expressions. That's all. So again, once again, I'm telling you, from the instruction set architecture, make these things, this schematic diagram, which is very simple. And from the schematic diagram, you just draw the micro operations, form the table, then the Boolean expressions. That's what it is. And here, I told you that some basic building block will be there, like ALU and all. This you can, when you will be writing your code, you can bring this ALU block, which is there, which is available, given with the software, like from Media Tool, you just call it and put it in a simpler fashion. You can design. This is a cell, basic cell. Okay, so that's what is a hardware control unit. And now, how the T state can be generated? T state is T1, T2, T3, etc. Let's assume that there are maximum 4 T states. Okay, of course, in this case, there are 6. So if it is 6 flip-flops will be required. I'm assuming that 4 T states. So first, what you have to do, forcefully, you make one of them 1 and rest of them 0. That is possible if you see that the upper diagram, PR, the red colored is written, and rest of them, these are with the clear bar. So if you give here is a 1 signal, then first one will be 1 and rest of them will be 0. And then since they are connected in that way, in the ring fashion, each time a clock comes, then what happens? First is 1, 0, 0, 0. What will be the next state? 0, 1, 0, 0. So look, here the clock diagram. Q0 is 1. After that, Q1 will be 1. All rest of them will be 0. Q2 will be 1. Q3 will be 1. By this ring counter, so you can generate these states. So Q0, let's say, call it T1. Then Q1 is T2. Then T3, T4. In that way, the T states are generated. So step counter is nothing but a ring counter, which will generate this T1, T2, T3, T4, T5, T6, and so on. And basically, for that, you need a basic clock. On the right-hand side, a clock is given here. If you see the diagram, here a clock is required. So from clock, you are generating, you are extracting the T states. And this is given in the control signal generator. From the decoder, what is coming? This is INS1, INS2, INST. So at a time, only one of them will be 1. Say, there are 4-bit opcode. Let's assume that 0000 is for low day. So when 0000, that is the opcode, then let's say INS1, which stands for low day, that will be 1, rest of them will be 0. And depending on the time and all the control signals will be generated. So this is your hardware control unit generations. So as far as the CPU design is concerned, first, you, with the schematic, with the registers, and all the control signal that needs to be generated. So from the standard cell diagram, your ALU, whether multiplier or adder, that depends on the instruction sets that can easily be designed. Okay, so just to derive the Boolean expressions as I've told you. And there are other techniques for designing that I'm not going to discuss right now because time is short. Microprogram control unit, that is there. Basically for CISC processors, microprogram control units were used. But now for the RISC architecture, these microprogram control units are not used because they are slower. And nanoprogramming was also there. With Motorola, in their VLSI chip design, they used the nanoprogramming technique also long time back. But I would have loved to talk about it, but we have shortage of time. Now let's go through the reduced instruction set computer. Now, as I told you earlier, that RISC architecture, the technique for designing this processor doesn't vary drastically from CISC. Only the architectural concept differs, not drastically in point of view. So that we have to consider. Now here, the RISC architecture, they comprise of few instances, relatively number of. Now question comes, why? If the instructions number are less, then the writing program will be very complex. These, that, many questions will come. So why do we require less number of instructions? Now, this is which critical. Now, if you write programs in high-level language, you will find certain things. Now, why I'm talking about the high-level language? Because ultimately you have to write the programs in high-level language, and a compiler will translate this high-level language into some machine code, which is understandable by the particular processor. Now, I believe you know, many of you, or maybe most of you, are quite accustomed to high-level language programming, especially C. But have you analyzed when you write your program? One thing just I would suggest you can check it or you can analyze it. When you write the programs, what type of instructions are very common in your code? The most common instructions are like A equal to, let's say, B plus C, or P equal to A into B plus C into D, or something like assignment statements are very common. Now, when you write A equal to B plus C, how it boils down to the machine level language. Load accumulator with B, add with C, store with this, etc. So most of the instructions you will find either your assignment statements or your arithmetic statements, or few will be some branch statement, because assignment statements you use frequently, but definitely branch statement you don't use that frequently, but you require definitely. Without that you can't write a program. Or some subroutine instructions you'll be using. But there are, apart from this, there are many other instructions which hardly you will be using. So it is found that 10 to 15% of the instructions which are used 80 to 90% of the time, don't you need to emphasize on those instructions which are used some 85 to 90% times or 80 to 90% times? The instructions which are not used frequently, discard them. If at all you require, then you should have some means so that you can make those using some other instructions. Like more instruction means your control unit complexity will be more. Now complexity will be more means more silicon area, because you will be requiring more number of logic gates, more number of transistors, more areas, more power dissipations, and more chances of failure. All these things. So if you discard those things and use less number of instructions, you are using huge silicon area. And you can use that silicon area in an efficient way. How? Like load and store. Assignment statement means frequently you have to deal with the data. You have to store the data onto the memory, or you have to read the data from the memory. So I told you at the beginning that storing the data in the memory is costly in terms of time. But if the data could have been stored within the CPU, the time would have been much less, because if the data are stored on the register, the access time will be much less compared to storing data onto the memory. But in the CISC architecture, number of registers are less. So we need to have larger number of registers. If we have larger number of registers, then those data, instead of storing onto the memory, would have been stored temporarily onto the registers. This is called load store architecture. So in the RISC computers, RISC processors, we have larger number of registers, because we have saved a lot of area from the control unit, and some part we can use for registers. That is the reason RISC processor has many registers. Okay, and is a streamlined architecture and fewer and simpler addressing modes. In the CISC architecture, you will find a lot of addressing modes. So cutting across all these things, you have few addressing modes like direct, indirect, immediate, register addressing. That's all. Okay, and all the instructions should be of same length. Why? Because it's based on the pipeline architecture. Now, what is a pipeline architecture? Let me just tell you the pipeline architecture. We have already discussed that for each instruction execution, there are 5 stages: fetch, decode, operand fetch, execution, write back. So let's say when the first, and all of them are, let's say, doing independently. So there are different hardware units. Fetch is one unit, decode is another unit, operand fetch is another unit. So they are working one after one. So typically in the CISC computer, if I assume that each unit takes 1 clock cycle, for executing one instruction will take 5 clock states. After 5, then the second instructions will be executed. So to execute the first and second will take 10. If there are n number of instructions, it will take n into 5 clock cycles. But if it is pipeline, then what will happen? Let's say when the first instruction in the fetch cycle, it has gone to decode cycle, then fetch unit is free. Then the second instruction can enter into the fetch. Then when the first instruction has gone into the operand fetch cycle, then the third instruction can be in the fetch. So in that way, after 5 clock cycle, first instruction's execution will be completed. Then after only one cycle, the next instruction will be completed. Then after one cycle, the next. So virtually it is happening when there are large number of instructions, only single cycle is required for executing. Okay, so you are getting huge gain in the pipelining. But to support pipelining, all the instructions should take equal amount of time for instruction fetching. So if if some instructions are 2 bytes, some instructions are 3 bytes, then instruction fetch, this time will vary. So to maintain that synchronity, if all the instructions are of same size, then there should not be any problem. That's why in RISC architecture, since it is pipeline architecture, all the instructions are of same size. So to support pipelining, and another thing is interesting, to support pipelining, you require separate address and separate instruction memory and data memory. Why? Look here. Let's say when second instruction is in the operand fetch, then what is happening? Instruction decode, instruction fetch. Here, when fifth instruction, if you see this diagram, when the fifth instruction is instruction fetch, means it is fetching the instruction from the memory, and the third instruction is doing opcode fetch. Opcode fetch also involves memory. So if the same memory is there, then operand fetch and instruction fetch cannot be done simultaneously. Isn't it? Because for third instruction is the operand fetch on the same memory, and for the fifth instruction, it is instruction fetch. So there is a clash. So to avoid the clash, what you have to do? Operand fetch involves the data, instruction fetch involves the instruction. So if there are two memory, then that clash will not be there. So that's why in Harvard University, this concept was conceived. So separate program memory and data memory. So that is the reason. It's not that for nothing we have made separate program and data memory. This was the compulsion. And here the control units are normally based on hardware control logic, because hardware control logic is much faster compared to microprogram control logic, because microprogram control logic is based on the memory. So entire control words are stored in the memory, and memory access time will make it slower. Okay. So Spark, PowerPC, MIPS, etc. are the RISC architecture. Example of this. So RISC processors are highly pipelined. Here some specs have been given to design 32-bit instructions of same length. So this in fact, this is an architecture design which was done by one of my students in his BTech project when I was in Delhi and was with HFCL. So that boy from IIIT, Allahabad, he did his work under my guidance and supervisions. So he was given this architecture, the RISC-V2 design. Exactly here, the way we have designed the CISC, exactly the same. First you design the instructions, from the instructions you make the architecture. Only thing here, program memory and data memory will be separated. So there are different buses. Two separate buses will be there. One for program memory address bus, program memory data bus. Another is data memory address bus, data memory data bus. Rest of the things are, concept is same, and how many registers and all you'll be using, that depends on your architectural design. Instruction set architecture. Here you just notice one thing at the top of the left hand side, blue colored box, register file. Here number of registers are there. Where in the CISC architecture, not many registers will be there. Okay. And another thing is here, since the architecture is pipelining, your micro operations flow will be slightly different. How? I'm just showing it. here microoperations flow like T1, T2, T3, T4, T5, all of them, they will be done at the simultaneously. Okay, that is the thing. And the rest of the things are same. So this is all about the RISC architecture. There are a large number of registers. Then you have to find out what is the size of the program memory and data memory. And here the instruction set was designed. But already time is over, isn't it? Would I proceed because it will take some time?
Yes, you can take your time. No issues.
But the people will. Okay, I'm making it short.
Oh.
It's very difficult, like RISC architecture, design of a RISC processor design in 2 hours is extremely difficult, but still. So there are, I'm just briefly, I will discuss about what are the hazards in the pipeline. So pipelining, already I have discussed pipelining. So there are 3 types of hazards.
Hello, sir.
Yes.
Sir, I am Tommy Chakraborty from CBCA, second year. Sir, I have a question that can I leave this meeting for now because my network issue is very poor. It is getting poor and poor. Worst and worst is going on.
Okay. You can just, I think, are you recording this lecture?
Yes, sir, we have a YouTube
Recorded.
Okay, you can contact later on. Okay. Anyway, so hazards in the pipelining. As it sounds nice, there are certain problems associated with the pipeline. There are 3 kinds of hazards in the pipeline, and that needs to be sorted out. Data hazards, control hazards, and structural hazards. Briefly, I can say you, data hazard is now. Let's consider that there are different units of the pipeline. Add R1, R2, R3, means add R2 and R3 and store in R1. Okay, and solve R4, R1, R5. Now, briefly, if you can see here that here R1 will be used in the first instruction, R2 and R3 will be added, which will go to R1. Now, this will go at the last stage, that means at the end of 5th clock cycle, R1 will be updated. But here, where you will be requiring? You will be requiring R1 when? At the fetch, decode, then operand fetch and executions at the 4th. And R1 is not yet been ready. And that time you will be requiring R1. Okay? Because R1 plus R5 means what? Executions. We have stages are what? Instruction fetch, instruction decode, operand fetch, execution, write back. So write back means R1 will be updated at the end of 5th clock cycles. And here, where you are requiring at the end of 4 clock cycles. So R1 is not yet ready. So that is the problem. To solve the problem, what has to be done? You give some time. So solution of these problems is in between these 2 instructions, use a no-op instruction. No-op instruction means it will not do anything, but it will delay. By that time R1 will be ready, it will get. So these are done by the intelligent compiler. So compiler, what will do when your high-level language will be translated into the machine code, and within that, when it finds that if R1, here it is used in the left-hand sides, like R2 plus R3 goes to R1, and same R1 is used in the next instruction, then there must be a delay. Okay. Or let's say these are instructions. To take this example. Okay, initially R1 equal to 11, R2 equal to 12, and R3 equal to 34. So first instruction is R1 equal to R2 plus R3. So R2 is 22 plus 3, it is supposed to be 25. So, but 25 will be generated at the end of this. Here they are using 4-stage pipeline.
Participants, please stay tuned. I think the network has got some problem on the speaker's end. So please stay tuned. Thank you. Participants are requested not to leave the meeting as because I think there is some network issue has gone some end. Uh-huh. Yes, ma'am, there is some network issue from sir's end, so we're checking into it. Kindly stay tuned.
Hello.
Yes, sir.
Hello.
So you're audible now.
Yes, sir.
So you're audible now, sir.
On. May not be there, but I will probably. Okay. Is it okay?
Okay, sir. Okay, sir. No issues.
Okay. Sure.
Okay, sir.
There are 3 types of hazards in the pipelining. One I discussed, that is the data hazard. hazards. Okay. Another is the second is the control hazards. If there is a branch instruction like conditional branch not equal to or
So
something.
excuse me, sir.
So
Kindly share your screen. So we can't see your screen.
yeah, screen is not to be shared from here. Okay.
Okay. Please give me.
Because it is there in my computer. So not much is left. So I'm telling verbally. Okay.
Okay, sir. Okay, sir. Okay, no.
Only one or two screens were left.
Okay, sir. Okay, sir.
Yeah. So what I'm saying, I was discussing about three kinds of hazards in the branch. Okay. One is the data hazards, as I told you, that let's say R1 equal to R2 plus R3, and next is again R1 will be required in the next instructions. So unless that data is updated, the second one will not get it. For example, R1 equal to R3 plus something. So this is the write back on R1. Write back will be done at the end of the 5th clock cycle. But in the next instruction, if again R1 is required, the data which is not yet been updated, then there will be a problem. So to keep some time, there must be no instruction if we need to. So if the first instruction is the data which will be updated, that is required again in the immediate instruction, next instruction, then in between two instruction, you give a no operations to give some time. That is one. Second is the control hazards. Control hazard is if there is a branch instruction like branch jump not equal to. So that not equal to calculation is yet to be done, but before that the branch is taken. So again you give some no of instruction in between. It is called delayed branching. You delay the branching. And third is the basically this is another hazard. This hazard is basically for pipelining. In a pipelining, if instruction fetch and data fetch has to be done on the same memory, there will be a conflict. To avoid that conflict, Harvard architectures are used, whether data memory and program memory should be made separate. That's what. So RISC architectures, they exploit all these things here. That is the reason in the RISC architecture, if we summarize, number one, less number of instructions, relies on load store architecture. That means number of registers will be very large to support this load store architecture. Then your pipeline architectures, and to support pipeline architecture, your memory, data memory, and program memory should be separated, and hardware control logic. So these are the features of the RISC architecture. Now in the advanced RISC architectures, it's happening. The instruction sizes are even 64 because most is can be supported, and point operation instead of integer instructions only. So all these are the advanced features in your advanced RISC processors. And some advanced RISC processors are used for DSP applications, digital signal processing applications, where some instructions like your FFT or finite impulse response filters, those kind of instructions are also coming and are also thought of. Directly will be given in the instructions. So these things will be implemented. But recent times, RISC-V has emerged. RISC-V is an open source architecture. In the sense, earlier all these architectures, they are the intellectual property of different companies. Either maybe Intel or maybe ARM or some others. But here, anybody can use that thing, this architecture. This is a very, very streamlined architecture. I suggest you can go through this open source architecture, the RISC-V. And in fact, in MAKAUT, some of my students, they have taken this project, this RISC-V architecture project. They are doing it. In case you are interested, I can share with you what are the work going on. So RISC-V is the latest state-of-the-art architecture for the RISC implementation of the RISC processors. Okay, so that's all from my side. Thank you very much for giving me an opportunity to deliver a talk. Thanks a lot.
Thank you, sir, for sharing such a knowledgeable talk, which is an asset for us. Go ahead and take some time for
Thank you,
questions.
sir.
Okay. In fact, here one of my colleagues from MAKAUT, Dr. Madhumita Dashalkar, she is also present over here. So you can also. I think she is ready for asking some questions, maybe. Anyway, if you have any questions, please feel free to ask me.
Good afternoon, sir. Can I ask one query of mine?
Yeah.
So firstly, thank you for sharing such a talk with us. It is very much beneficial for us to have some research on this topic. And so one of my queries is that you have said about the Moore's law. So one thing we have seen that the dimensions of the chips are getting diminished day by day. So actually, in the
can't
current
hear you.
scenario,
I can't hear you. In fact, some noise is coming. Cool.
so is it fine now?
Yeah, now it's okay.
So is it fine now? Hello? Okay.
Yeah,
So
it's
actually,
okay.
yeah. So my question is that, so in the current scenario, sir, we have seen that the chip dimensions are getting diminished day by day. So now the current technology is working in about a 5 nanometer to 3 nanometers, and the Moore's law is getting devoid. So my question is that, then what is the future of Moore's law? Since it's getting challenged day by day, so what is the future
Yeah, I'm
ultimately of the
telling you,
Moore's law?
Moore's law is no more valid today. No, Moore's law is no more valid today. Okay. If that law is not valid, doesn't matter. The sky is not going to fall, does it? Because technology doesn't depend on Moore's law. Moore's law, okay, roughly looking at that statistically, we are saying that this is the predictions in that way. It's not following. How does it matter?
Yes. Yes, sir. Okay, sir. Thank you.
Okay, any other?
Hello, sir.
Yes, please.
Why CMOS device conducts strong 0 and weak 1?
Yeah, if you see that CMOS device, how it operates. If at the gate, okay, if you give a 1, then what happens? You get it 0 totally, isn't it? If you give 1, then only it will be 0. Say drain and source. Source is connected to the ground. Then what will be the drain voltage? If you give 1 at the gate, you will get 0. Now threshold level, the voltage this minus VTH, that factor you have to consider. When you take a PMOS circuitry, in PMOS, in the gate you have to give 0. Then only your source, in the drain if you give 1, VCC or VDD, then that VDD minus VTH that you will be getting. So is it exactly, VDD you are getting, not minus something? So that's why it is not. You get my point. Here for 0, you won't get the strong exactly 0. It will be subtracted from that. For if you take a PMOS circuit, in a PMOS gate, what voltage you have to give? 0 or 1? Tell me. Which voltage you have to give? You have to give a voltage 0. Then only the transistor will be on. Isn't? Then only the transistor will be on. And if the transistor will be on, then what you will get? Once it is 0, if you give the input 0, then will you get exact 0 voltage? But if you give VDD equal to high, that voltage you will be getting. In the VLSI circuit, have you gone through this? What is the VTH voltage? What is the threshold voltage? What is the level of that? Any other?
So we have shared the question page to you. I mean,
Yeah, you can.
The audience had queries. So they have got a bit of queries.
A few questions
so
you can ask now, I can tell.
Yes, sir.
So one or two questions I can answer right now. Okay,
yeah,
one or two
sir.
questions you can ask now.
Yes, I'm selecting few of them. One person short the question. He has asked that why what side of a processor is always in the power of 2 and why other than that is not possible. Does instruction size depend on the word size of the processor?
No. Look, word size. First, let's come about the number of locations. Okay, so I would say the number of locations must be power of 2. Because number of locations are given by the address lines. Is it or not? So let's say
Yes.
there are 4 locations. How many address bits will be required? Log of 4, log of 2 to the power means 2. If there are 8 locations, 8 means 2 to the power 3. 3 address lines will be required. But as far as the word size is concerned, there is no such restrictions. But what we define 8 bit as a bit. 8 bit is what? 1 byte. So byte 1 byte, 2 byte, 3 byte. In that way, if we define, then automatically it will be coming in terms of 8 bit size, isn't it? And 8 is what? Is the power of 2.
Yes.
So 8 bit, 16 bit, 32 bit. In that way, it will be coming. Do you get my? Hello?
Hello.
Yes, sir.
Do you get me what I'm saying?
Are you getting sir's answer? The person who was posted.
Yeah.
Yes, sir.
Okay.
Hello?
Okay. Sir, hello. Shorita Goswami, are you there? Are you getting the answer, sir? Has answered your query right now? Are you there?
Yes, yes, yes.
Okay.
I have got.
Okay.
Yes, yes.
Okay.
Because the number of locations has to be in the power of 2. Okay? 2, 4, 8, 16, 32 in that way. And number of word size, typically it is in terms of byte. So each byte means 8 bits. So 8 bits, 16 bit, 32 bit, in that way, the words are basically given. Okay.
Okay, sir.
So one of my students is having a question. One person is Monikanchan Beda. He is from the current 3rd year. He has asked the question, what is debugging?
What is?
Debugging.
Debugging means, checking the faults, basically.
Okay.
These days, most of the processors, they have some IEEE JTAG port are there. JTAG means Joint Test Action Group under IEEE. So here, there are some to scan, boundary scan method is there to check whether there is any fault in the CPU
Scan.
or not. So debugging is a process to find out the fault. Okay.
Okay.
Okay, sir. Okay.
Another question is another from our student, final year. Parasitic capacitance always good or bad for VLSI design? He is Shuvendu Mundol. He is from final year of our college.
No, it's not. Look, it's not the question of good or bad. When the parasitic capacitance is there, we make the equivalent model of the transistors. We consider those things. Okay?
Okay.
Because it is there. Parasitic capacitance, you cannot avoid that. It must be there. In some sense, you can use it in a positive sense.
Mhm.
Okay.
Another question is from from Pradeep Day. Here he has asked, which is the high level representation of VLSI design?
Sorry? High level?
Representation of VLSI design.
High level representation means what? When you do the VLSI design, you have to express that using a hardware description language, isn't it? And hardware description language is like, VHDL or Verilog or System C. Using that, you will express your entire design.
Yes. Yes, sir. Pradeep, are you there?
And this is another thing is some tools are there where entire schematic diagram you can give, And from schematic diagram, you can get also the VHDL code. So that kind of advanced level tools are also available.
Okay. What is slack in VLSI? This is asked by SK Mohammed Aryan Romi. What is slack in
What
VLSI?
is?
Slack in VLSI. Slack. SLSC, slack.
FLAK.
Slack.
Okay.
SLSC.
I don't know what he means by that. I couldn't understand it.
Mohammed Aryan Romi, are you there?
Yes, sir.
Please ask your query to sir. I mean, the question you have posted is what is slack and what's your query? Please ask, sir.
What do you mean to say?
So
Elaborate. I don't know about this particular term.
What is slack in VLSI?
What does it mean? Slack means what do you mean to say? Where from you got this word? I've not heard about this term.
But I think there are many PhD scholars also in the audience. Are you all having any questions? There are many PhD scholars also in the audience there.
Excuse me. Hello.
Oh, yeah.
Yes.
Okay.
Sure.
Hello.
Yes, please.
Hello.
Yeah. I think Slack is something related to timing. I think. I mean.
Okay. Okay. If it is something related to timing, I'm telling you, there are two things. In VLSI, the timing delay is a very important thing. We call it fixing of the timings. For an example, I'm just giving a simple example. So let's say you have an AND gate. And AND gate, there are two inputs. One is X, another is X bar. Okay, and input is a pulse. What will happen? If I ask you what should be the output? An AND gate, one input is X, another input is X bar. What is the output?
0, 0.
Yes. Huh?
AND gate
Hello?
is 0. 0.
Yeah, that is wrong, in fact, I'm telling you. Apparently, it seems that X and X bar so 0. But in practice, it is not that. What is that? Let's say your input is going from 0 to 1. Okay, a pulse. It was 0. When it was 0, X was 0 and X bar was 1. It was 0. So when X has gone to 1, but X bar is yet to go to 0 because of the timing delay of the NOT gate. So for small time, both the inputs are 1. Understand?
Yeah, absolutely. Yeah.
So what will happen? For that period, both the inputs are 1 means what will be output?
1 output, high.
1 output. For how long?
For the it's a static one error, right?
Gate delay of the NOT gate, isn't it?
Yeah, yeah.
So this is a problem. This is a problem.
Yeah, absolutely.
So this is called the hazards, basically. We call it hazards. Okay. So these hazards will be there for asymmetric path. When you design the VLSI, then due to this asymmetric path, asymmetric means what? The AND gate, upper one goes straight away, but the lower one has to go through a NOT gate. So it takes some time. So when you design a complex logic functions, there will be many such things, and these kind of problems will be there. So these timing fixations has to be taken care of, and there are certain techniques to solve this hazard problem. These are called timing hazard. Okay.
Yeah, understood. Got the point.
So that's it.
Sir, I have a question.
Yes.
So, actually, sir, we have discussed in a very short time, though, we have discussed about you have discussed about the RISC architecture. But, sir, within this discussion, I couldn't get how pipe hardware can be implemented in RISC pipelining architecture.
This can be implemented. In fact, look, this pipe can be implemented over here. Basically, for any vector kind of instructions and all, that can be used. And many people, they are using it. In fact, RISC, since it's open source architecture, there are many ways of implementing it. It can be used. That's not a problem.
Actually, sir, I'm trying to get how pipe can be implemented in the hardware. Is there any shift register sort of thing or any kind of other?
Pipe easily can be done. It's very similar to this, the way you are doing one after one. Let's say the data is going from one to next in that way, pipe flow. Okay, that can be done for data cases. It can be done by using some shift registers. Shift register means in each clock from one, it will go to the next one and so on. And these are basically for vector process.
There is a modification in controller sequencer unit.
Controller sequencer, look, controller design. When you'll be trying the controller, first you fix your instructions and all that you'll be doing. Based on that, your controller will be designed, isn't it?
Yes, sir. Controller pattern also will be generated. Now I am asking that when we are going for a pipe architecture, so we must have a modification in the control word pattern, so then we can generate the pipe instructions by sequencing and controlling in both ways.
Yeah, in fact, what I suggest, you first fix your instructions. What are the instructions? Because pipe that will be used, based on your instructions, isn't it? Basically,
Yes,
to
sir.
augment,
Yes, sir.
enhance the speed of the instructions, you are going to the pipe, is it not? Hello.
Yes, sir. Yes, sir. Voice is breaking. Sir,
What I'm asking,
again, can.
yeah, yeah. Now can you hear me now?
Yes, sir. Yes, sir. Audible.
Yeah. What I'm saying, you are going to use the pipe for enhancing the speed of your instructions, isn't some instructions?
Yes, sir. Yes, sir.
Yeah. Let's say you have some vector instructions. Vector instructions are there in the RISC file. Yeah. So you want to do the vector instructions. So there it has to go through the pipes. Once
Yes,
it
sir.
goes through the pipes, then what you have to do, you first circle your instructions. And then how these instructions will be executed in the pipe, based on that, the microcode will be generated. Okay?
Okay, sir.
So your micro operations have to be indicated. And based on the micro operations, different control signals have to be specified.
Okay, sir. So when we are generating the micro operations and write the state table, so should I keep the state table or the micro operations instructions within a LUT, or there is any other way,
No,
sir, to
LUTs
keep
are not, for RISC, LUTs are not used. For RISC,
then?
LUTs are not used basically because it will be slower. LUT means what? The memory access.
Yes, sir.
And the
Yes, sir.
memory access is always slower, isn't it?
Yes, sir. Yes, yes, always, sir.
So that's why there any hardware RISC architecture are based on hardware control logic. Okay.
Okay, sir. Okay, sir.
And to reduce the complexity, what you do, number of instructions are restricted to a minimum.
Okay. Okay, sir. So anybody has got any questions from sir? Anyone?
But I think we are having over here Mrs. Muthuita Das Sarkar with us, assistant professor from Department of VLSI in MAKAUT. Ma'am, are you there?
Who?
Muthuita Das Sarkar, madam. Ma'am, are you there?
Does he have?
Ma'am, it's a pleasure to have you here. Are you there, ma'am?
Yeah, he's there.
She is
She
muted.
muted.
Okay. Oh, she muted. Okay.
She's there, I think.
Just
Muted
a
by you.
minute.
She's muted by you. Just.
Provi, please unmute. Provi, please
Yeah,
unmute.
they're unmute. They will unmute you.
Ma'am?
Yeah.
Madhumita, ma'am? Are you here?
I think she must be here.
Is she unmuted?
Has she been unmuted?
No, she has not unmuted.
Achha, in your electronics, the VLSI is there, is it?
Yes, sir. Yes, sir.
In which year?
So currently the VLSI is in the 6th semester for the 3rd year in the current new MAKAUT syllabus.
Yeah, and she is there. She is asking some questions.
No, sir.
Hello?
Yes.
Yeah, I can hear you.
Hello? Yeah.
Actually, I have joined firstly from desktop computer, and that's why the problem is there. So I am now joining with my mobile. So I have no questions, sir. I have heard all the things you have elaborately discussed, and I think the students are very much illuminated with the details of the talk. And Shoumo is also a student, so I think Shoumo can appreciate that recent advancement that you were talking about is really very good. One thing I just not my questions, it is my query, not query also. It is my inquisitiveness that the hardware control you are talking about that to make the pipelining. So in that case, as the instruction set are minimum, so can we actually predefine the what are the states to be in the no operation state, and what so that the balancing and the data hazards to be minimized predefinedly, and depending on that, can we define the hardware like this? I
In
don't
fact,
know. I'm just asking.
yeah, I'm telling you. Yeah. Can you hear me?
Yes, sir. Yes.
Yeah, I'm telling you one thing. This is a problem. When you are doing the pipelining, then what is happening? Let's say a data R1, let's say R1 equal to R2 plus R3. R1 equal to R2 plus R3 means R1 is a register which will get the data after the execution of R2 plus R3, and this will be done. This will be done when at the write back operation. Write back means on the register the data is written, and if the immediate next instruction wants to get the data, because of the timing, it will not get the time, because writing of the data is completed at the end of 5th cycle, and this is requiring at the beginning of the 4th cycle. So to avoid these things, if we just make a delay, that means to access the data, it waits for some time, means one delay. Then there is no problem.
So at the time of operation itself, it will be taking.
No. It is what happens, at the compile time, compiler will check, and the theory there is a theorem for that. If there are two subsequent instructions, consecutive instructions, such that one variable is at the left hand side and the same variable is appeared in the right hand side, then there needs to be a delay inserted in between two instructions. That is a standard theorem. Means, let's say R1 equal to R2 plus R3, R4 equal to R1 plus something. So before R1 has been updated, the next instruction wants to get that R1 value. So what it has to do? It has to wait for some time. So how to make this wait? By inserting a delay. That is the thing. So these are done by software.
Okay. Only by software it can be possible. Okay.
Yeah.
Okay.
Only by software. And intelligent compiler, they do it.
Yes, you are talking about intelligent computing. Okay.
Yeah.
So in that case, during the time of
RISC
operation, if it feels that there is a kind of iterations, the dependent and the independent function, and that means the right hand side is depending on the.
Yeah. No, it is done. It is done before that. Before executions, the compiler does it and put it in that. For RISC architecture, these are the important things. For data hazards, this is a very common thing. Another thing is a jump. Jump to something. Conditional jump. If A equal to B, jump to that. But A equal to B, that is yet to come. Next instruction. So that's why it's best to.
Again, there will be delay until that execution.
Yeah, so that it can get some time. There is another technique also, branch predictions. Branch predictions I have analyzed. In many cases, there could be wrong result also. Then there will be a penalty. Like you just assume that it will go there.
No, prediction is not always
that
100% correct in that case.
Yeah, it is not always correct.
Okay, thank you, sir. Thank
So
you.
there are three things.
Yes.
You are saying something?
No, sir. It is. Okay. I have absorbed all the things that you were told already.
But the thing is that this lecture is of 80 hours lecture course. I had to do in 2 hours.
Yes, that is a long. Yes, it should be series of lectures. Then students can learn everything in detail. Okay.
And another thing I've noticed, some students were asking me about very fundamental things that I think in the basic electronics they should know that in a transistor, when saturated or
yes,
cut off,
that is a very common question.
Yeah, then the threshold voltage. These things are the very fundamental things that they should, isn't?
Yes, yes, sir.
Indeed, sir.
Like switching is on doesn't mean that that voltage will be there. Some VTH has to be subtracted.
Switching, that means that it is close to saturation, means close to zero. Maybe may not be exactly.
Yeah, exactly.
But point towards are sometimes near to zero.
All right. So anyway, we'd love to discuss all these things because since your engineering college is affiliated to our university, we will be glad for any kind of improvement suggestions. If we can contribute, we'll be glad for that. And let me tell you finally, one thing from our sides. We have our microelectronics and VLSI technology department. It offers two courses, two MTech courses. From this year, one additional
embedded
courses.
and one
Earlier,
also,
we had
yeah.
only one course.
Embedded added. Embedded.
Microelectronics and VLSI technology, what Dr. Madhumita Dashalkar, she was taking care of for a long period.
Yes.
Okay. Like after 2012, when I left MAKAUT, she has been doing these things. And anyway, even though I'm looking after, but she is actively doing all these things along with myself. So we're jointly working on that. So two courses we are offering. One is MTech in Microelectronics and VLSI technology. Another is VLSI and embedded systems, which is being started from this year. Okay. So you can just convey it to your students and all, so that, and
Yeah,
we can
many
guarantee
of my students are they are wanting to get admitted to in-house MTech. So they have asked me to get some information on, and I've told them to give the PGET properly, so they get admitted and get
one thing
graded by
and
given.
we are offering the best possible technology to our students, in fact. And if you see the track record of our
indeed,
students, many of them are working in
Yeah.
Xilinx, many of them are working in Intel. So
Yes.
it's a fantastic track record.
Yes,
And our VLSI course was the first time it was offered in the state of West Bengal. I remember that I was there at that time. I started from 2003, perhaps. Yeah, 2003 December. This was the first time of this kind of courses, and we used to get students from various parts of the country, Tamil Nadu, Odisha. So
various parts of India.
we
Yeah,
have written that.
indeed.
Okay. So these courses and will cover various parts of embedded systems and VLSI, like digital signal processing, computer architecture, processor architecture. And one of the best things in our course, like a student who will be graduating from our institute, they will be completely learning how to design a chip. Okay, be it for processor, be it for digital signal processor, mixed signal processors, and many new things we have introduced which are not offered elsewhere, like switch capacitor based design. Okay. Then looking the importance, keeping the importance of mixed signal processing in view, that also we are offering. But our ultimate objective is to go for VLSI design for this. That is a course.
Exactly.
So you can convey it to our students and
Yes.
can go through our websites. Okay. So that's all is from my side.
So I request all the audience over here. So kindly please switch on your cameras for a group photograph. It's a ritual from our end. Kindly please everyone switch on your cameras for a group photograph. As we come to the conclusion and we move over to our respected head of the department, Mr. Vajraji Sarkar, for the vote of thanks. Please switch on your cameras, audience, for a moment, for a group photograph. Participants, kindly switch on your cameras, group photograph moment. Our student coordinators, switch on the cameras. Is it done? Okay. Is it done? Okay, so I give the honors to our head of the department, respected head of the department, Mr. Survacharji Sarkar, to give the vote of thanks. Thank you. Over to you, ma'am.
Okay.
First of all, I want to thank Professor Dr. Amitabha Sinha sir for such detailed analysis, starting from the basics of the processor, instruction set, addressing modes, and all the analysis he has given. That is very fruitful and very effective for our students. Actually, they have just learned the microprocessor basics and few concepts of computer architecture. But most of the students have not yet completed the details of VLSI and microelectronics part. So, sir, your lecture will motivate them towards the study of VLSI technology. and how VLSI technology can be used to implement RISC CISC architecture. And it is from my request, sir, we have to go for another 2 or 3 webinar so that they can well understand about the fact if it is possible for your end. Sir, it's my personal request that if it is possible to manage your busy schedule from your busy schedule, that we can go for another 1 or 2 webinar. And I want to thank our honorable chairman, sir, for giving us the permission to conduct this webinar, and our executive director, sir, and director, sir, to give us the supports, all required instruments, resources, net connectivity, and all the things they have provided us to conduct our webinar successfully. Not only that, our participants, our students, our in-house students and the other students coming from the other colleges, they have listened so intensively, and they have so many questions they are asking in front of sir. So I'm also very showing my gratitude to all the participants present over this online platform. During this pandemic situation, it has become very difficult for the students to keep patience at all the times. And we are also, teachers are getting sometime fatigued that we cannot convey the utmost of our knowledge and we can deliver the lab sessions to them. So only through this webinar get so motivated. And from your side, sir, I am very much thankful to you. And that's all from my side.
Okay. Thank you.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, everyone, for joining.
Okay.
Thank you, everyone. Thank you. Have a good day, everyone.
Thank you, sir.
Okay.
Thank you.
Thank you, sir.
Thanks everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Participant, please submit feedback form. Those who have not submitted.